Okay, so today we are going to have a lecture on the design, principles, and applications of optical tweezers. My name is Carlos Bustamante, and I would like to tell you about how is that optical tweezers work, and what are the principles on which they are based, and what kind of applications you are able to use optical tweezers on. Now, the name optical tweezer was given by Arthur Ashkin to a device that he invented in the 1970s while he was working at Bell Labs. And the idea is to use light in order to manipulate objects, physical objects. It turns out that particles with high index of refraction relative to the medium, as you may imagine is the case with plastic beads or glass beads or oil droplets, are attracted to intense regions of a laser beam, which is focused through a microscope objective, and can be held permanently at that position, at that focal point. And this is the discovery that Arthur Ashkin made in the 1970s. In fact, here you see a paper that was published by Arthur Ashkin in 1970, where he describes the single beam trap or single beam optical tweezers instrument. It's also called an optical trap, and the double beam optical trap, as indicated here. They found that if they collimated or they focused a light beam through to a diffraction limited spot in a cuvette that contained many small beads, plastic beads, it was possible to actually trap momentarily those beads. But for a single trap, they found that those beads tended to be pushed along the direction of propagation of the light, as indicated here. And so they developed the dual trap beam in order to have another force of the light, actually, that was propagating in the opposite direction in order to obtain a stable spot for trapping the bead in the center between the two beams. Later on, in 1987, Ashkin continued developing the idea of the optical trap, and in this case, with the idea of using the optical trap or the optical tweezers to trap and manipulate single cells. And so they were able to show that they were able to trap live bacteria, they were able to sort living cells from non-living cells, and even manipulate organelles inside the cells. In this particular publication in 1987, they also realized that instead of using visible light, they were to use infrared light. It was possible to, in fact, decrease and diminish the damage that the radiation could actually do on the biological systems. Now, the principle or the fundamental physical principle behind the idea of the laser tweezers or optical tweezers is the fact that light exerts force on matter. And in fact, in 1619 already, Johannes Kepler suggested that the solar repulsion of the finely divided matter that comes off the tails of a comet is due to the pressure of light exerted by the light coming from the sun. And so, as you see, this idea is very early. Newton considered this idea in his optics book and considered it plausible. And later on, eventually, James Clerk Maxwell, when he developed the 4 equations that describe all the theory of electromagnetism, was able to, in fact, predict theoretically that light should be able to exert pressure and forces on matter. However, the first experimental demonstration in the laboratory for the evidence of radiation pressure, as it's also known, given the fact that this works not only with light, namely with radiation that we can see with our naked eye, but also with infrared light or with UV light, in other words, with radiation of any wavelength, is due to Lebedev, who published a very influential and important paper in the Annalen der Physik in the year 1901. And you can see here that the title of his paper is, in fact, First Experimental Evidence for Pressure of the Light on the Solid Bodies. Now, in order to understand how that optical tweezers work, we need to actually describe the trapping in two different regimes, the trapping of objects by light in two different regimes. The first regime we are going to consider is the regime in which the wavelength of light is much larger than the size of the object that you want to trap. Imagine, for example, using wavelength of visible light and you are trying to trap an atom or a molecule, a small molecule. Okay? So we call d the size of the object, lambda the wavelength of light. And I remind you that light can be seen as nothing else but electromagnetic radiation that travels in space, and that electromagnetic radiation, essentially, when it is polarized, means that you have an electric field that is vibrating in a particular plane, in this case the vertical plane, and then a magnetic field that is vibrated in the horizontal plane. Okay, so what happens when you collimate or you focus light, say through an objective? You take light from a laser, you fill the back focal plane of your objective, and then you collimate it into a diffraction limited spot. What is going to happen is that you're going to have a situation like this, where you have the light, in fact, much more intense at one particular region, which happens to coincide with the axis of this cylindric shape, and also at the center of the cylindric shape. So if you have an object, a small molecule, for example, or an atom, that is nearby, as indicated here, what is going to happen is that the electric field of the electromagnetic radiation is going to induce an electric dipole moment in the molecule. And that's what we call here mu, right? You see here we are calling mu as the electric dipole moment generated in the molecule by the electric field of the light. And it turns out that an induced dipole moment will be attracted towards the higher intensities of the light indicated here. So a force, which I indicate here with this arrow, will actually act on the molecule and will bring the molecule, in fact, towards the center of the beam. Okay, so you see that in the small size limit, therefore, we can explain the trapping of objects by light simply as the coupling between an electric dipole moment, which is induced by the electric field of the light, as indicated here, right? Again, here you can see that the electric dipole moment can be written as, for an object, any object, an atom, a molecule, any object that has a polarizability, that is polarizable, and is described by, whose polarizability is described by this quantity alpha, then the electric field of the light will generate the electric dipole moment. It turns out that the energy of this object in the field is given by this quantity, minus 1/2 the induced dipole moment times the electric field, the external electric field, and we can, of course, write the dipole moment here as alpha times E. So we obtain the square of the electric field, which is proportional to the intensity of the electromagnetic radiation, as shown here. In other words, the energy of the dipole in the field, E, is proportional to the intensity of the light, right? And now, because we have now this dipole moment essentially in a potential energy field due to the electric field, then it is possible to calculate a force as minus the gradient of the intensity, as indicated here. Okay? So essentially, the force that the dipole experiences is proportional to the gradient of the intensity. So in fact, if the beam is not homogeneous but is being collimated by an objective, right, then what you will see is that the dipole moment will be attracted to the most intense part of that beam. And that's what we call the gradient force. Okay? So that's what we call here the gradient force. Okay, so to summarize, if you have a dipole moment, a molecule, an atom, and you have it close to one of these intense beams of light that have been collimated and focused through an objective, what you will see is that a force appears that is essentially pulling the dipole moment induced in the molecule, right, towards the center, the place where the beam is most intense. But besides this attractive force, if you wish, that we are observing here with the gradient force, there are other kinds of forces that are also present when the object is small compared to the wavelength of light. For example, incident light, as shown here, will hit on the molecule or on the atom, and it will be reflected by the molecule or the atom. It will be essentially scattered away. And it turns out that because light carries momentum, right? Remember, light carries momentum, and each photon of the light carries an amount of momentum that is equal to the Planck constant divided by the wavelength of light. Then what is going to happen is that these photons that actually were coming, in this case, from left to right, and hit the atom, are going to be bounced back. So they have lost their right momentum. And the result is that because momentum, linear momentum, is a quantity that is conserved in nature, just like energy is conserved in nature, then somebody else has to gain momentum in the right direction, and that somebody else turns out to be the atom itself. Okay? So it's just imagine as if you are actually playing a game of pool, and then you come with some ball that hits the white ball here with one angle, it gets reflected, and of course the other ball, the white ball, will actually move in the opposite direction because it's trying to conserve momentum. Okay, so this is therefore a reaction or recoil force that we must take into account as well. Okay, so let's try to formalize a little bit what we mean by this recoil force that, as I mentioned, has to do with the fact that light carries momentum. In fact, I want to remind you first that according to Newton's second law, what we call force is nothing but the rate of change of momentum of a system, right? Mathematically, that can be written in this way, where you can see that the force is nothing but the derivative of the momentum of the system with respect to time, the rate of change of momentum. Now, let's assume that we have n photons coming and they are coming towards a surface per second, and each one of them carries a momentum h, I told you, the Planck constant divided by the wavelength of light, and that these photons are going to be absorbed by this surface, which they are actually hitting on, right? Then what is going to happen, of course, is that each photon was bringing momentum p equal to h over lambda, and now, at the end of absorption, all the momentum of the photon is absorbed into the object, so that the momentum of the photon goes from p to 0. In other words, it has a change of minus p, right? It has lost, each photon has lost a momentum, an amount of momentum equal to minus p. Okay? So we can actually write that in this way. We can say that the object, the surface in this case, is going to experience a force, a pressure due to the light that is equal to the rate of change, again here, notice, the rate of change of the n momenta h over lambda that were coming from each photon to hit the surface, right? And of course we can write the wavelength of light as the frequency of light divided by the speed of light times the index of refraction of the medium. So we have this expression, and if you look carefully, we have here that you have n, number of photons per unit time, times the h nu, which is the energy of each photon, so that turns out to be actually the power, W, of the beam. And so you see that the force that is experienced by the surface due to the absorption of the photons is actually equal to the power of the light hitting the surface, which is energy per unit time, times the index of refraction of the medium divided by the speed of light. Okay? Now, of course, this assumes that everything worked perfectly, that no photon was scattered, for example, that all photons were absorbed. So in practice, people often write this expression in terms of some kind of empirical efficiency factor epsilon, which multiplies the quantity that we have derived here, because to take into account the fact that some photons are not absorbed, some photons were reflected or scattered or so on and so forth. But the important thing is the following. You see how the fact that light carries momentum means that if these photons either are absorbed and therefore they lose completely their momentum on a surface or on an object, the object or that surface are going to gain that momentum that the light had, and therefore are going to actually experience a force, given that the force is nothing but the rate of change of momentum. In other words, how the momentum changes in time. Okay. In the small size regime that we are discussing here, when the object is much smaller than the wavelength of light, still it's true that you have, therefore, two types of forces: the gradient force that I talked before, which is proportional pretty much to the radius cube of the object, and you have the scatter force, or the pressure force, or the momentum force, if you wish, that is proportional to the radius to the 6th power of the object. And really, if you want to trap stably any object using that is very small compared to the wavelength of light, say an atom or molecules, you have essentially to balance these two forces to make sure that you obtain stable trapping. One solution, for example, is to increase the numerical aperture of the lens, as you will see in the other regime, and this will tend to reduce the focal spot, make it smaller, and increase the gradient force to the point in which it can overcome the scattering force. Anyway, so let me now go to the second case. The second case is in the limit in which the object is much larger than the wavelength of light, as indicated here, right? So d is much greater than lambda, and in this case, it is not possible to describe the interaction in terms of gradient force or scattering force, but it is possible instead to describe the interaction using ray optics. And so, what happens when light hits, say, a plastic bead, a polystyrene bead, or a glass bead? What you know is that the object, in this case, the bead, is going to then reflect the light, refract the light, or scatter the light, okay? So we must consider all these three effects. As I said before, in this regime it's no longer possible to separate the gradient force and the scatter force, but we can still understand how the trapping takes place by using conservation of linear momentum, which we have been already talking about, okay? So ultimately, of course, stable trapping requires that all these forces that arise from all these phenomena, namely the scattering force, the refraction, and the reflection, would be balanced so that you obtain an object physically, mechanically trapped. But let's remember some of the ideas that we've been talking about, okay? So, what happens when a photon meets a refractive object? Imagine, in this case, we imagine that we have a bead, and this bead is placed in the beam, in the path of a beam, and so there is a number of photons that are coming towards the bead, right, as indicated here, and each photon brings a momentum h over lambda, so that's the incident momentum of the light. It hits the bead at this position, it gets refracted, as indicated here, right, and again gets refracted as it comes out of the bead in a different direction for what we call now momentum out of the beam, right? So notice that the incident momentum of the light has now changed into the outgoing momentum of the light, and there is a change in momentum of the light corresponding to delta p, okay? So the light has essentially lost an amount of momentum that is proportional to this arrow here, delta p, okay? So, because momentum is conserved, the object, which is the bead, has to gain momentum now in the same amount, but in a direction opposite to the direction in which the light had lost. And so, you see that essentially because momentum is conserved quantity in nature, then the rate of change of momentum, or of the light, actually is equal to the rate of change of momentum of the object with an opposite sign, and the rate of change of momentum, of course, is a force that acts on the object, in this case, this arrow that actually tends to kick the bead upwards, in this case, and forward. Okay, so now that we can see that we can use ray optics to understand how light acts on objects, it is possible to then see two different regimes. Imagine that you have a beam. This beam actually has a Gaussian profile. So I want you to imagine that this beam is more intense in the center, just like in any laser pointer. The center of the beam is much more intense than the outer layers of the beam, right? The periphery of the beam. Okay, so here, imagine now that this center of the beam is up here. So this is the profile of intensity of the beam. Notice it's not much light coming on the periphery, but then as you get towards the center of the beam becomes more and more intense, and then presumably you can imagine that this continues symmetric towards the other side, right? So it will eventually decay. So there is a Gaussian profile of intensity in the beam. Okay, now let's assume that a peripheral ray actually first hits the object, in this case this plastic bead. So what is going to happen again is that the bead is going to refract the light along this line and then refracted it again, as you see here coming out. The light used to bring momentum downwards, only had momentum downwards, right? But now notice the light ends up with a momentum that is less downwards and partly towards the right. Okay? So the light has lost forward momentum and has actually gained right momentum, right? So the result of that is that the bead, because of that beam, is going to gain momentum forward to compensate for the momentum lost by the light, and towards the left in order to compensate for the momentum gained by the light in the rightward direction. Okay? Okay, so you might tell me at this point, okay, so now you just showed to me that if you have a bead that is not centered in a beam of light, the bead will be kicked out of the beam, right? Okay, but that's not the story, not the complete story yet. You see that now we have to do the analysis of what happens with photons that come very close to the center of the beam. There are many more photons here because it's much more intense, right? The intensity of the beam is much higher at the center of the beam. And these photons will be refracted, and we will have a more or less symmetric situation here in which the light, these photons also have lost momentum downward and have gained now momentum rightward, right? So now what is going to happen is that the bead is going to gain, in order to compensate for that loss of momentum, you are going to have momentum downward, okay, down, and also towards the left, in order to compensate for the momentum gained by these photons towards the right. So notice, you have this force that appears due to the peripheral beam, and then you have this force that appears due to the central beam rays. And you can see that the net force is going to be essentially in this direction, because there are many more photons actually coming this way than coming that way. So the net force is to grab this bead and center it like this towards the center of the beam. And this is why plastic beads or glass beads are actually, that are in the periphery of a laser beam, are immediately centered into the center of the laser beam. This is the trapping we are talking about. But notice one thing, that the bead is not only centered at the center of the beam, but it's actually also pushed a little bit downward, because the net force, remember, is going to be also downward, partly. So that means that the bead is going to be trapped, centered in this case, but is going to be actually pushed along the direction of propagation of the light. And that's not good, because we want to trap this bead stably, right? So it turns out that this case is the case when you use light that comes parallel from the beam, that is not focused, okay? So that's what happens when you have very, very poorly focused or not focused light. The case we want to consider then is the other case, which is shown here on the right, where you see that now we have the beam. You have again the Gaussian profile of the beam, right? It's more intense in the center than in the periphery, right? And now what we have done is we have centered the bead and we have put it exactly at the center of the beam. And so you can see that a peripheral ray now is going to be refracted, notice, in this fashion. And on the other side also the peripheral ray is going to be diffracted on this fashion. The light was bringing, notice what happens now. The light was bringing, this beam for example, was bringing momentum from left to right. And now ends up with a momentum from left to right, but less momentum from right to left. And instead it has gained momentum downward compared to what it had originally. Okay? So the result of that is that the bead is going to experience a momentum in this direction towards the focus of the beam. Okay? So the bead is going to be, if you wish, sucked up towards the focus of the beam, because having opened the numerical aperture of the lens the way we have opened it in this case, we have inverted the direction of the force acting on the bead. So you see that now, if you use a very high numerical aperture lens and you put the bead in the center, that bead is going to experience forces from both sides that actually are trying to levitate the bead towards the focus of the beam. Okay? Of course, you will have also some light that will be reflected, like shown here in the dashed lines, for both beams, and that light is going, because it's now gaining momentum backward, is going to produce a force that is pushing a little bit the bead along the direction of propagation of the light. So in the end, all these forces have to actually balance each other in order to produce a stable trapping of the object in the beam. So to summarize, what I want to say therefore is that if you want to trap an object that is larger than the wavelength of the light, and you want to trap it in the beam in a stable fashion near the focus, then what you want to do is you want to use a high numerical aperture lens, as shown here, which will produce forces that both tend to pull the bead toward the focus of the light, and that will also push a little bit the bead due to scattering, due to reflection, and that hopefully you can actually balance those two forces, and of course, in that way, you can obtain stable trapping. Notice that the stable trapping position that I showed you in that diagram is located just below the focus because, of course, of the scattering force, which is actually pushing the bead a little bit downward, right? Now, if instead of having a plastic bead or a glass bead, you use, say, a bubble, now it turns out that the index of refraction of the particle is smaller than the index of refraction of the medium, because air has an index of refraction smaller than water, and then what happens is that everything I told you is still true, except that all the direction of the forces invert, and so you have what is called a metastable system, and it's not very good for actually trapping objects. Experimentally, we find that if you place a 1 micrometer bead in an infrared laser, essentially about 3% of the power of that laser actually can be converted into a trap force, as indicated here by this expression, okay? Okay, so in fact, this demonstration that having a high numerical aperture lens allows you to stably trap an object without having to use two counter-propagating beams of light, as originally proposed by Ashkin, was also published in the 1980s by Arthur Ashkin and in collaboration with Steve Chu, as you see here. In this important paper, they show that it is possible to correct for the scattering force or the reflection force by actually using a high numerical aperture that will essentially produce a force, as indicated here, that will actually pull the bead towards the focus of the beam. And here is a movie that actually I'm going to show you where we have a bead that is trapped. You can see the bead in the center is trapped in an optical trap, and on the side there is a pipette. The pipette carries another bead, or we can use that pipette to actually manipulate that bead in the optical trap. And what I want you to see is the relationship, the inverse relationship that there is between the position of the bead and the position of the beam, due to this conservation of momentum, of light momentum. So please, let's see that bead. Now you can see that the bead is here in the center of the trap, and now here is the pipette, and we can use the pipette to suck the bead out of the optical trap. See? There, you see? And see how, as we apply force on the bead, the light moves up, and when we actually apply force up on the bead, the light moves down. That's precisely the conservation of momentum between the bead and the light that is the principle of optical trapping.